Next example is a coaxial problem. We have two circles with the same radius. In the inner circle, the potential is equal to a constant value phi1, and the outer circle we have a constant value of this potential equal to phi2. So on all over this circle, the value of the potential is constant, and the same for the inner circle. So this is a typical problem where we use Laplace equation in polar form, because in this case we can assume that the solution of the problem is only dependent of the distance from the center. So it's only dependent of the radius r. Let's recall that the Laplace equation in polar form takes this form. So here we have r squared multiplied with the 2-time derivative of phi with respect to the radius, plus r multiplied with the derivative of phi with respect to the radius, and plus the derivative of phi 2 times with respect to the angle theta. So theta is this angle relative to the positive x-axis. In our case, we can assume that, as I mentioned, this term is 0 because there is no dependence in the theta direction. Therefore, we only have two terms in this Laplace equation. So we have r squared multiplied with phi rr plus r phi r. This should be equal to 0. So what we are doing next is we are dividing with r squared in each term. And next we divide with phi r. So since we do not have any dependence in the theta direction, we can just write phi prime prime as we usually do when we only have dependence in only one variable. So instead of writing phi rr, we just write phi prime prime. Similarly, instead of writing phi r, we just write phi prime. So then this equation reduces to this equation. And the reason for writing the right-hand side and left-hand side on this form is that it's very easy for us to see that the left-hand side is equal to the logarithm of phi r and taking the derivative of this expression. So just check for the left-hand side. If we take the derivative of the logarithm of any variable, we obtain 1 over this variable multiplied with the derivative of the variable. And 1 over the variable is just 1 over phi prime. And the derivative of this kernel phi prime is of course equal to phi prime prime. Similarly, on the right-hand side, 1 over r is just equal to the minus 1 over r is just equal to minus the minus logarithm of r, and taking the derivative of that expression. So what we have here is that the derivative of this guy is equal to the derivative of this guy, which means that this must be equal to this plus some constant which we called a tilde. Now if we know that the logarithm of something is equal to some expression, then we can take the exponential function of this logarithm. And what do we get then? Then we get just the phi prime in this case. So what I've done here is just to take the exponential function of the right hand side and the left hand side, and then we obtained this expression. So the exponential function of a sum of two terms is just equal to the product of the exponential function of the first term and the exponential function of the second term. So what we do here is we are observing that the exponential function of this constant must of course be some new constant which we called a, and this should be multiplied with the exponential function of minus the logarithm of r. So what we can do next is just to notice that minus the logarithm of r is equal to what? Is equal to the logarithm of r in minus 1. So that's what we have done here. Now we can just reduce this expression to 1 over r, or what we write here is r in minus 1. So now we have reached the conclusion that phi prime is just equal to this constant a multiplied with 1 over r. So we conclude that phi must be equal to this constant a multiplied with the logarithm of r plus this b. And this is due to the fact that if phi prime is equal to a constant multiplied with 1 over r, then this phi must be the logarithm of r multiplied with this constant plus some new constant. So then we have the general expression written here. In order to find a and b, we just have to use the boundary conditions, this phi 1 and phi 2, and this gives us two equations with two unknowns, and this is very easy for us to compute exactly as we did for the previous example.